3, Jun E 1.
So it's my turn?
Yes.
Okay. Can you see my screen?
Yes.
Okay, my question is 5. At time t equals to 0, the brakes of a car are applied to a car traveling at 22.2 meters per second. The car decelerates at a constant rate of 20 minutes per second square. Calculate how far the car travels before it comes to a stop. First we have at equals to negative 20 because it's decelerator, and we can have Vt by integral at get negative 20t plus c. And for the question, the V0 is equal to 22.2, so C is equal to 22.2. Vt is equal to negative 20t plus 22.2. And we can get xt from integral Vt equal negative 10t squared plus 22.2t plus c. And by the question, it comes to a stop, so x equal to 0 is equal to 0. The c is equal to 0, so xt is equal to negative 10t squared plus 22.2t. When car is stopped, the Vt is equal to 0, so Vt equals to negative 20t plus 22.2 equal to 0. The t is equal to 1.11 second. So plug in the 1.11 to xt, we can get the position is 12.321 meters.
Okay. I have a question.
Uh-huh.
I cannot write on this. You have x of 0 equals to 0. So this point, where did you get this point?
Because the car, we want to find how far the travel. So at first, the car is at the stop point.
Oh, okay, I see. Okay. So I see. Right. The car, right, with the car, before the car start moving. So you use this. Great. That's very smart. Right. Okay, that's very, okay. Thank you,
Thank you.
Yinping. All right, that's fine. David, your turn.
I think I need permission to share.
Oh, I didn't. Oh, okay. Yes. Okay, now you can present.
Okay. Sorry, I'm trying to.
No problem.
Okay. Sorry, it's taking a long time to upload. My internet is not that good. Okay, so I have 1.1.3. Yeah, so here, can you see it?
Yeah.
Okay.
It's very blurry.
Huh.
Yeah, maybe because you use a pencil.
Maybe. I'll use pen for next homework then.
Okay, thank you.
Sorry about that. So for 1.1.3, we're given the initial acceleration, initial velocity, and initial position. And so you can take the integral of the acceleration because it's just dx squared over dt squared. And so if you integrate twice, you'll get the position, but you need to factor in the constants. So first you take the first integral, and it's pretty standard. You just put a t next to the -2, and then you add the constant, and that's the velocity. And you know velocity at time 0 equals 10. And so you can there solve for c from there, and then that will give you your velocity equation. And then you take another integral, and then when you do that, you have another constant, and then you know when at time 0 x is equal to -4. And so you can do the same thing again and take one more integral, and that will give you the position function. So yeah.
So your position function is a downward parabola, -t squared plus 10t minus 4?
Yep.
Yeah, okay. So when you present, you need to tell us, right? You need to tell us your result.
Oh, my result?
Right, you're presenting. You don't really have to read through all the calculations, but right.
Okay, I'll do that next time. Sorry.
Okay, all right. Okay, so that's David. Junyi, question 1.
All right. So, Professor, can you hear me?
Yeah.
Okay, so I'm presenting question 1, which given question is dy over dx equal to 2 over x to the cube, and given y of 1 equal to 3. So I take the integral dy dx. I use the power rule with the integral 2x to the -3 dx, which is equal to the -2x to the -2 over 2 plus c. So I got -1 over x to x squared plus c, and plug in the 1 into the y, which is equal to -1 plus c equal to 3. The c is equal to 4. So the final equation I got is y equal to -1 over x squared plus 4.
Yeah, okay.
Thank you.
Thank you, Junyi. All right, so those 5 questions from homework 1. So for the rest of you, no one has any excuse because homework 1 is done for you. 5 people presented. And so now we will have Ryan talk about one question from little homework 2. And he picked 2.7. And Ryan, because this is new to us, you basically have to teach us, all right? You basically have to teach the rest of us. Okay, Ryan, your turn.
I'll try my best.
Okay.
So my question was 2.7, and it basically just asks us to find the particular solution to the differential equation. And the differential equation is right here. The bottom was really the only place that I could fit it. So if you take a look, you're going to see that we have, right here, we basically have y prime. That's the way I look at it, at least. We have the derivative of y in terms of x. And then on the same side of the equation, we also have y and y. So you might be wondering, if we integrate this whole side, because it's just a sum, right? We can break it up and integrate each part. So if we were to integrate that, what would happen? Well, we'd have y and then plus, what are we integrating with respect to? Well, if we do x, then, what happens to those y squareds? If we do dy, then we have the integral of y. If we don't know what y is to begin with, how do we get the integral? So actually, it might seem a bit counterintuitive, but this dx, which I'll just move up here, this dx can actually be moved to the other side. However, there's a bit of a prerequisite. So the first thing to do is to take the original function and basically separate the x's and y's. And that's not always possible. But in this case, because we have y squared on both terms, we can basically pull it out. So the first thing I did was move everything to the other side except the derivative of y. Then I pulled out y squared. And so now what we could do is we could divide by y squared, and we can multiply by dx. And now that does seem a bit strange, but what ends up happening is we have dy over y squared, or y to the negative 2 dy, and then we have dx times all of this. We can then integrate both sides, but we integrate on one side with respect to dy, and the other side with respect to x. And so that basically gets rid of dy and dx for both sides. And so doing the integral, it's fairly easy for this one. It ends up being negative 1 over y plus c1 equals negative x cubed minus x squared plus c2. And now both of them are just constants. So if we were to, since they're both numbers, if we could just move this to the other side, because we don't really know what it is yet, we'll just have one number. So that's exactly what I did. I solved for y, and I also just combined the c's because it's one constant we're solving for. And then this becomes the general solution. So in order to find the particular solution, I took the function and I plugged in 1. And I did that on both sides, obviously. And since we know from the question y1 equals 3, this just becomes 3. And on the other side, it becomes 1 over 2 plus c. Of course, at that point, c is pretty easy to solve for, and that's negative 5 over 3. So the general solution still has the constant term in it, and the particular solution is the one that gives us y of 1 equals 3. And if you were to graph it, which I have done, here we have y equals 1 over x cubed plus x squared minus 5 over 3, which is our particular solution. And as you can see, right at 1, comma 3, there's our point. And when you actually plug this in, if you have the calculator do the derivative for you and y is just a function, you can actually see there's a red line on y equals 0 because it always equals 0.
Great. Okay, Ryan's presentation, because it's advanced, but it leads to our new material today, which is something called separable differential equations. All right, so that's great. Let's go to our notes. Okay, separable differential equations. Just like what Ryan has, but Ryan question starts with dy over dx minus this capital letter or plus capital letter h of x comma y equals to 0. Well, in this case, it's a minus, right? Then Ryan moved over a negative h of xy to the other side. Separable means this capital letter h of x comma y can be written as a product of two functions. And one function is in terms of x, another function is in terms of y. In Ryan's presentation, question 7, we have y squared as h of y. Then the rest involves with x, so that's g of x. So you see, we can separate into a function, two functions, product of two functions. So then what we can do is, just as Ryan did, right? We divide by g of x. Of course, it cannot be 0, right, on both sides. Or in this case, we divide by h of y, because we want to leave dy on this side. We divide by h of y on both sides. So we have 1 over h of y dy. You see, this part is all in terms of y. Then we multiply dx on both sides. So we have g of x dx. Right? Because this is a function in terms of y, dy, this is a function in terms of x of dx, and they equal each other. So we can integrate the equation, can integrate both sides simultaneously. One with y, because this is just function in terms of y. And we integrate this because g of x is just a function in terms of x. Right? So this is for separable functions. If it's not separable, we may not be able to do this. Let's see an example. In this case, the example we have dy over dx equals negative axy. We see this is a function, well, we can treat this. We can treat negative ax as g of x and y as h of y. And we are given the initial condition, y of 0 equals to 4. So we just do that, right? We divide by h of y on both sides, which is y. We divide by y on both sides. We get dy over y. We multiply dx on both sides. So the right-hand side becomes negative ax dx. Well, this is just 1 over y dy, right? Now so this side is in terms of y, this side in terms of x. So we integrate, because that equation, so we can perform operations simultaneously on both sides. So we integrate both sides. Well, 1 over y, integrate, we get ln of y, but the ln takes positive. We have a function for ln, for log functions. The domain has to be the domain has to be positive, right? So that's why we put absolute value around y, just to force y to be positive. Then plus a constant. Then we integrate to negative ax, that's negative 4x squared, plus another constant. Again, just like as Ryan did, we move those two constants together. We could call C3, or we just call C. So we get an ln, absolute value of y, equals to negative 4x squared plus a constant. Well, then we rewrite, because we want to solve for y, right? We just rewrite as e to this power. Right? Or we can rewrite this equation as e to this power. That's absolute value of y. So absolute value of y equals to e to this power. We can separate it into two terms, to e raised by negative 4x squared times e raised by a constant. So this would be our general solution, right? E to a constant is just a number. We could just use C or A to represent a number here. So this is a general solution, right? And then we're given an initial condition. So y of 0 equals to 4, we can substitute in. So y of 0, absolute value, equals to 4, equals to this. Then we can solve for A. We can solve for the number A. So A equals to 4. Then, so we get a particular solution. So y, absolute value of y equals to 4 e to the negative 4x squared. Okay. Y of 0 is greater than 0, positive. So we don't have to worry about y being negative, right? Because of y of 0. Remember the domain of Ln. So, right? So we have a particular solution as y equals to 4 e to the negative 4x squared. Anyone has any questions?
I have a question, Professor.
Yes, Gregory.
Sure. I think I blinked. What's going on with the A, above when we do the multiplication of E and E?
What do you mean? This A?
Mm-hmm.
Well, this A is e to the C3, or e to the C, e to a constant. So E is a number, C is a number, so e to the C3 is a number, so we just use A to represent.
Okay. Great.
Yeah.
Thank you.
You're welcome. Any other questions? All right, let's see second example. Well, dy over dx equals to 5 minus 4x divided by y times 4y squared plus 2. And then we're given an initial condition. So we see those two can be separated, right? Can be separated as 5 minus 4x, as a function in terms of x. Then 1 over 4y cubed plus 2y, that's a function of y. So we're treating this one as g of x. We're treating this one as h of y. Then we can do the same thing. We multiply dx on both sides. We divide by 4y cubed plus 2y on both sides. And of course, maybe we better write y cannot be 0, right? Y does not equal to 0. If we want to be mathematically accurate, we would put a y not equal to 0 here. Then we integrate both sides. We integrate the equation, right? Which means we integrate both sides simultaneously. Integrate this, we get a y to the 4th plus y squared plus a constant. Integrate this, we get a 5x minus 2x squared plus another constant. We can move those two constants together. We could call C or C3. So we'll have y to the 4th plus y squared equals to 5x minus 2x squared. So this is a general solution, right? It's not of a function. It's not one function itself. It's just an equation. Because we have y to the 4th power, we have y squared. So this is new to us probably. So the solution to the differential equation are not only one type. All right, so here we see the solution for this differential equation. Solution for this differential equation with this initial condition is this equation, right? And definitely this equation is not a function. It's not one function. But then we're given this initial condition, so we can substitute this in to get the constant value. Okay, let's read this remark. One cannot easily solve this equation for y in terms of x. So we leave the solution as it is, right? It's an equation, that's okay. This equation represents a set of curves in the xy plane at every point that face this equation. It doesn't have to be a function, right? Notice if you differentiate this equation implicitly, right, we will get this. Because with the equation, we can use implicit differentiation. Once we do that, we get back this dy over dx. With the initial condition, we can plug in, so we get a constant value to be 17. Now we have, with the initial condition, we have a particular equation. So the constant is 17 now. Okay, anyone has any question? So this is new, right? This is new to us. The solution does not have to be a function. The solution can be an equation. Okay, let's see this example. So we have this y dy over dx minus this term equals to 0, right? So we move this term to the other side. We have y dy equals to positive term of this. Then we can simplify this. So a raised by 1/3. A is 2 cubed raised by 1/3. That's just 2. Then x squared raised by 1/3. That becomes x raised by 2/3. Then y raised by 1/3. Right. Then we want to put a y raised by 1/3 to the other side, and we want to put this dx on the right hand side. So we have y divided by 1, y over 1/3, dy dx equals to this. So 1 minus 1/3, that's 2/3. So we'll have y to the 2/3 dy equals to x to the raised by 2/3 dx. We integrate the equation, which means we integrate both sides simultaneously, because again, this is in terms of y, this is in terms of x. That's why we could do that. Integrate this by power rule. We get 3 over 5, y raised by 5 over 3, plus a constant. Integrate the right-hand side. Get a 6 over 5, x raised by 5 over 3, plus another constant. We combine those two constants. Then we can simplify this equation. Multiply by 5. So y raised by 5 over 3 equals to this plus a constant, right? Just a constant. 5 over 3, C3 is still constant. So then we can take the root of 5 over 3 on both sides. So solve for y, because this is odd, right? Because especially the power is odd, also the index is odd. So that guarantees we can solve y, then y is a function in terms of x. If this is even, you know, especially if the index is even the numerator, right? We may not able to do that. But in this case, yes, we can. The solution is a function. So y is a function in terms of x. We're not given initial condition for this, right? So this one, we're not given initial conditions. So we just want to find the general solution to this. So the general solution to this differential equation is a function. Is a function. Right. Anyone has any question? Let's see this example. This one we want to find a particular solution because we're given this initial condition. So e to the y dy dx equals to 3e raised by 3x minus 2y. So we need to separate the exponents of e, then put the y terms on the left-hand side, then the x terms on the right-hand side. So this can be broken into 3e to the 3x times e to the negative 2y, right? Then we divide by negative e, we divide by e to the negative 2y on both sides. So e to the y times e to the negative 2y divided by e to the negative 2y is the same as multiplied by e to the 2y. So that becomes e to the 3y. Then multiply dx on both sides. So we have e to the 3y dy equals 3 e to the 3x dx. We integrate the equation. So integrate e to the 3y, we get 1/3 of e to the 3y plus a constant. Integrate 3e to the 3x. We get e to the 3x plus another constant. Combine two constants. We have e to the 3y equals 3e to the 3x plus a constant. So we rewrite this equation. We write this equation as a 3y. We take ln, right? We take ln on both sides. So we have 3y equals ln 3e to the 3x plus a constant. Divided by 3 on both sides, so we get a y equals 1/3 of ln of this term. So that's our general solution. Then with the initial condition, y of 0 equals this, so we can plug in for x to be 0, and the y value is this. So y of 0 is this, plug in x to be 0, get a 1/3 of ln 3e to the 0 plus a constant. Then we have 1/3, we have ln. So this is a 5, this is 3 plus a constant, so the constant has to be 2. So our particular solution for given initial condition is a function. It's this. Y of x equals 1/3 of ln of 3e to the 3x plus 2. Anyone has any question? Okay, let's see how do we use this in life applications. Population growth or continuous compound interest. So it can be modeled with this rate of change, dp over dt. Right. K times p of t. Okay, so let's see. So dp over dt equals the k times p of t, which is treating p of t as a function, and k is just some annual growth rate, a number. All right, k is just some number representing annual growth rate. Separating the variables, so we get 1 over p dp equals to k of t dt. Integrate both sides. Integrate this, so we get ln of p plus a constant, kt plus a constant. So ln p so equals to kt plus constant. Okay. So we can rewrite this one as e to the kt plus c3 e to the kt plus a constant equals to, right? So P equals to, so P equals to e to the this power. So that's our P. So e to the ln P is just P. So P is a function in terms of T. P of T equals to e to this power. But what is e raised by a constant? It's just some number, right? And we could use a constant to represent that. So we use C4, or before we use capital letter A, we can still use capital letter A here. Would be A times e to the kt. And if we do that, we see that's compound continuous interest, compound continuously formula, right? So that's our general solution. If the initial value, we use P of 0 equals to P naught. So then we have P naught as the C4 at this scalar here. So we write as a P of T equals to initial P e to the kt. This formula is familiar, right? Okay, anyone has any questions? So for compound continuously interest or population growth, so we have this dp over dt equals to kp. Or this 1 over p dp equals k dt. All right, let's see next example. The population of a town in 2010 was 100,000. The town's population in 2013 was this. So A, find the annual growth rate, which is a K times K. B, how long does it take for the population to double? That means P naught for P of T equals to 2 times P naught. P naught is the initial value. So P of T equals to, this is P naught, initial population, times e to the kt. So we'll have this P of 3 years, because the starting year is 2010. So 2013 will be the 3rd year. So that means P of 3 years later, the population is this. So P of 3 equals to P naught times e to the 3 years. Okay, so we use this to solve for K, for the annual growth rate. So we divide by 100,000 on both sides, get this. We take ln. So 3K equals to ln of this. We have to use a calculator. And ln of this is about 0.3. So K equals to 0.1, about, right? Approximation. So which means the annual growth rate is 10%. For B, double, for it to double, right? Double means, because the initial population is 100,000. Double means 200,000. Then, so K value we know now, K equals 0.1. We want to solve for T. We want to solve for how many years it takes to double it. So we take ln2 equals 0.1 T. We divide by 0.1, same as we multiply by 10 on both sides. So T is 10 times ln2. And so T is about 6.93 years. So about 7 years to double the population. Okay, anyone has any question? Okay, another application is radioactive decay. And we have dN over dt equals negative Kn. All right. So N represents amount of the what do you call it? The elements. All right. K is annual decay rate. So dN, so we rewrite this one as a dN over N equals a negative K dt. So K is just some number, right? So dN over N negative K dt. We integrate both sides, get ln N equals a negative KT plus a constant. Right? We rewrite this equation as E raised by this power equals to N. So we say N is a function of T. So N of T. So E to the constant, right, can be written as a constant. So N of T equals to some number multiplied by E to the negative KT. And then we recognize that's a decay, right? Decay. So that's a general solution for N. If N naught equals N of 0, so we substitute N of 0. So that's just a constant. So N of T, so we can write it as N of T equals N naught, initial value, E to the negative KT. So this is a particular solution for the initial value to be N naught. Anyone has any question? So for radioactive, so we have this dN over dt equals a negative Kn. Let's see example. Different elements have different decay rates. For example, carbon-14, which is used in estimating the age of some objects, has an annual decay rate of K equals to this. A piece of charcoal turns out to contain 58% as much carbon-14 as a sample of present day charcoal of equal mass. So what is the age of the sample? So we use the formula, right? So 58% can be written as 0.58 N naught equals to N naught e to the negative KT, and K we know is this number. So N naught divided by N naught, we can get rid of N naught. We have 0.58 equal to E to the this. So we can solve for T. And take ln on both sides. So ln of 0.58 equals the negative of this, negative KT. Divided by negative K, we have T. So ln of this divided by negative K. So T is about 4,480 years. Anyone has any question? Okay, continuously compounded interest. If we start with 1,000, so initial principal, and the 6% interest rate compounded annually. Then after 1 year, we have principal, right? The principal itself, and plus the increase the interest, right? 6%, 0.06. So after 1 year, we get $1,060, right? Because the interest 6% of 1,000 is just $60. So this is annual compounding. So after 2 years, So after 2 years, now this is our principal for second year. And times, so this is the principal itself. This is the increase, the interest part. So we can rewrite this one as, so 1 plus 0.6 is 1.06. We have this multiplied by itself. That's just this square. So for 1,000 times this one square, when we calculate, we get this much. Compound means the interest becomes your principal for the following year. So it keeps going. So we have this. After t years, we have the principal, the initial value, multiplied by 1.06 raised by t. If the interest is compounded twice a year, so annually, then after 1 year we have this. Right? Remember the formula? So with 0.06 divided by 2, so this is the principal part. This is increased by the interest. Then after 1 year, so we have, because this we have RT, NT, or you will call it N, because compounded twice, right? Twice. So 2 times 1 year, so this is a 2. So we get this much money. So after t years, so we get a 1 plus interest divided by 2, then raised by 2t. If we compound it monthly, so 12 months in a year, so this would be 0.06 divided by 12, then raised by 12t, so on and so forth. So for general annual interest rate of R% compounded n times per year, we have this one. Initial principal times 1 plus R divided by n, because R is annual interest rate. Annual interest rate, right? Divided by n, how many times it compounds, then raised by nt. If we invest 1,000 at 6% annual interest rate for 3 years, the amount we have at the end will depend on how many times per year it compounded. Right? Compounded once, get this. Compounded twice, get this, because 2 times 3, that's 6. Compounded 4 times, or 0.6 divided by 2, that's 0.03. Compounded 4 times, because compounded 4 times is 0.06 divided by 4, that's 0.015. Then 3 times 4, that's 12. So we get this much. So on and so forth, compounded every day. So this is compounded every day. This is compounded each month. This is compounded each quarter. Right? Compounded every day. So we get this, 0.06 divided by 365. Then raised by 3 times 365, which is 1,095. And we get this. So when the times of compounding increase, so we get more money, right? And compounded continuously, this is compounded continuously, right? We use E. What happens if we let the number compounded periods per year n goes to infinity? So that means compounded continuously. Every second you think of it, your money in the bank or in the institution is being compounded, which means the interest rate is being calculated. So let's take this, right? We take a limit, let n runs to infinity. So this is R divided by n, then raised by nt. And then what is the limit of this? What is the limit of n goes to infinity? 1 plus r over n raised by n over n, n raised by n over r. That's the definition for E, right? That's how E is Euler number. E is Euler number. It can be approximate, just like pi. Right? But it's an irrational number. So this is the definition of it. Right? But usually we have, but usually it's not as this complicated. Usually it's a 1 plus 1 over n raised by n. But in this case, we just have this r involved. But in any case, r over n, n over r. Right? If you want clearly, we can use m substitute n over r. So we see now this is exactly the definition for Euler number. Limit m goes to infinity, 1 plus 1 over m raised by m. David, question.
Yeah, this is about the interest that you started with. You said why is it that after 2 years of annual compound interest, you have a different amount than of 1 year of biannual interest? Wouldn't that just have compounded twice in both cases? Why isn't it the same?
No, it's different. When you compound it once, right, the interest is only being calculated once per year. When you compound it twice, the interest will be calculated twice.
Right, but in the example before, you do compound once per year, but you do it for 2 years, and then you do compound twice a year and for 1 year, and you get 2 different answers.
That's true. They should be different.
But in both cases, you compound twice, right?
Yeah, but it's different. But it's different. You see, this is compounded once for 2 years. That's how we calculate. You see here, it's 0.06 divided by 1 because n equals 1, and raised by 1 times 2. Okay, let's go to the general. Here, that's the formula. When you compound it once, n equals 1. You see r divided by 1. Then this is 1 times t. So when t is 2 years, but n equals 1, what do we have? We have 1 plus r raised by t. But if we compound it twice for 1 year, what do we have? We have r divided by 2 raised by 2. You see the difference?
Yeah, I see it. Thank you.
You're welcome. Okay, so we're here, right? So when we compound continuously, so E is involved. So how is E gets involved? Compound continuously means let this n run into infinity. So limit of n runs to infinity. And this is exactly the definition of E, Euler number. So that's why, so when compound continuously, we have this. We have the initial value multiplied by E raised by RT. Anyone has any question? Gregory.
Sorry, I think I forgot.
Don't be silly. Ask question. Questions
Yeah,
are
no
good.
problem. Yeah, I kind of forgot what R was for. What's R again? The
Oh,
percent?
R is annual. annual interest rate, right?
Okay.
It's annual interest rate.
Okay. Thank you.
You're welcome. Right? You see y has to be divided by n, so compounded n times. So this is not the annual interest rate. But when we compound it n times, we need to find the interest rate for the particular n. But the R itself is the annual interest rate. All right, so notice this. So we have this, right, formula. A of t equals to A naught e to the RT. A naught represents the initial value. R represents annual interest rate. T is how many years? And this satisfies this differential equation. dA over dt equals to R of A of t, right? Because when we differentiate this, we got dA over dt. Differentiate this, we got R times A naught e to the RT. Well, R times A of t. Right, A of 0 equals to A naught, the initial value. So R is the annual continuously compounded interest rate. The R just annual interest rate. So you see, so this R times A of t. So dA dt equals R times A of t. Let's see this example, how we use it. Suppose we start with $1,000 in an account where the money is continuously compounded at annual interest rate of R. So after 3 years, the amount of money has grown to this much. So we want to find out the annual interest R. We just plug in the values. Right? A naught is 1,000 initial value. A of 3 equals this much. So A of 3, right? 1,000 times E raised by R, 3R. So get this, we take a ln on both sides. So ln of this equals to 3R divided by 3 on both sides. So R equals to about, approximation, R is about 3.67%. Any question?
Hi, Professor. I have another question from the previous. When we're doing the derivative, you said, of A naught e to the power of RT. Yeah.
Right.
How does that equal R of AT again?
Oh, okay. Let's take derivative of this in terms of t. In terms of t, we're treating R as a number. So remember e to the RT, when we take a derivative, that's R e to the RT, right? Okay, let's bring to the whiteboard. Let's go to the whiteboard. So we have A of t equals to A naught times E raised by RT. So those two. So take a derivative. Take a derivative, we get dA of t over, I'm going to write over, we're taking derivative in terms of t, dt equals to, let's take derivative on this side. Well, A naught, still A naught, because it's a scalar. Over the E term, when we take derivative of the E term, we get R times E to the power of RT. Right?
Yes.
Yes. So what is A naught times e to the RT? Do you see that's just A of t?
Mm-hmm.
Right? That's just A of t. So that's why we get R times A of t.
Okay, I was concerned with the A naught, but it's just any point, right?
Well, just initial value.
Yeah.
Just initial value.
Okay.
All right.
Great. Thank you. Great. Thank you so much.
You're welcome. You're welcome. Okay. Newton's law. Newton's law for cooling or heating. The rate of change of the temperature of an object T being immersed in a medium of constant temperature A is proportional to the difference of A minus T. So dt over little dt equals to the K times A minus T. So T is the temperature of the particular object. And the A usually is the temperature of surroundings, right? So this is just being immersed in a medium of a constant temperature A. So you could just think A is the temperature of surrounding. Sometimes, well, let's see some examples. So it's proportional to this. That means this. Proportional means this, right? It means we have a scalar. So dt over little dt equals to this proportional A minus T. Let's see this example. A roast initially at a temperature of 40 degrees Fahrenheit is placed in a 400 Fahrenheit oven. You see which one is T, which one is A? A is the temperature of surroundings. So A in this case is the oven temperature, 400 degrees Fahrenheit. And what is T? T is the object. The degree of the object is 40. So A in this case, no, T is 40 degrees Fahrenheit. So for us, A minus T would be 400 minus 40. At 5 p.m., after 90 minutes, the temperature of the roast is 150 Fahrenheit. So we want to find a formula for the temperature of the roast after 10 minutes. Then so when will the roast have a temperature of 160 Fahrenheit? We just use the proportion equation, right? So dt over dt equals to K times 400 minus this object. So because A we want to find a formula for the temperature, right? But initially is 40, so this is initial value. We just want to find for any 10 minutes the temperature of the object for any time. So this is the temperature for the object in any time. So dt over little dt equals K times 400 minus this T. Well, of course, we're going to separate this, right? We're going to divide 400 minus T on both sides and multiply dt on both sides. So we get this 1 over 400 minus T dt equals the K dt. Then we integrate both sides. Integrate this side, we get ln of 400 minus T. Then this side we get kt plus constant, of course with constant, right? Of course with constant. But because this will have 400 minus T, so when we integrate, we have to offset with a negative sign because this is a negative T. We have to offset with a negative sign. So then this negative ln equals to kt, or ln of this term equals to negative kt with a constant. And the minus a constant or plus a constant doesn't really matter. We just remember this is a constant term. We rewrite this equation as e to the ln of 400. Okay, so we get an e to the negative kt minus c3 equals to 400 minus c, right? So this is in take e on both sides of the equation. We don't have to do that. We just rewrite this equation, right, as exponentials. We get a 400 minus t equals to a constant times e to the negative kt. So then we can rewrite it. So we move negative t to the other side. We move this one to the other side. So we get a t of t, little t, equals to 400 minus this e term. So this is our general solution. And with the initial temperature of 40 degrees of Fahrenheit, we can get the constant value, right? Constant value. So we substitute in 0 for t. So we get a constant equals to 360. So we get a particular solution, which is a function in this case. So capital letter t in terms of time t equals to 400 minus 360 e to the negative kt. Any question? Let me know if I go too fast. Okay, so B, we have B part. When will the roast have the temperature of 160? Well, given T of 90 equals to 150, that means we calculate, right? We use this. If we calculate, we will get T of 90 equals 150. Oh, this is still part A. No wonder I was like, oh, what's going on? So the first part, we're given after 90 minutes, the temperature is 150. So after 90 minutes, the temperature is 150. So we just plug in T for 90. Then we get this. We take ln on both sides. We solve for K. So K equals to this number. So we get a T of T, we get a function of T, capital letter T, in terms of T time equals this, 400 minus, we get this function. So B, just find after how many minutes object temperature will be 160, right? So that means the T of T equals 160, and we want to solve for T. So we get an e to this term equals to 2/3. We take ln on both sides. So T is about 100 minutes. 100 minutes. Which we go back to the time, because we started at 5, 100 minutes, which is 1 hour, 40 minutes later, which is 6:40, right, p.m. Because we started with 5 p.m. 100 minutes is 1 hour, 40 minutes, so that ends up 6:40 p.m. Anyone has any question? Anyone has any question? Yes, David.
Yeah, this is more just like maybe algebra question, but for part A, I don't understand why that ln needs to be negative.
Oh, okay. We integrate, right?
Yeah, right
Think
there.
about this. Right. Think about this. If we take a derivative of this, ln of this, do you see you get a negative 1 over 400 minus t by
Ah,
changing?
I see.
So you have the offset with the negative sign.
Okay, thank you.
You're welcome. You're welcome. Any other questions? All right. If no questions, you are free bird. Go ahead, start your homework.
Thank you. Have a good night.
Oh, you too. So your homework 2, part 2. And you have more questions this time. You have 11 questions.
Thank you,
Okay.
Professor. Have a good night.
You're welcome. Have a good night.
Okay, see you on Tuesday.
See you.
Good night,
Right.
Professor.
Yes. Good night. Thank you. Thank you. I'm going to stop recording.